The Ocean Beneath the Ice. The purpose of this essay has been to reframe how Antarctica is understood within the broader story of planetary oceans. For much of modern scientific history, Antarctica was viewed primarily through the lens of climate science. Its massive ice sheets regulate sea levels, reflect solar radiation, and influence atmospheric and ocean circulation patterns across the globe. Within this framework, the continent appeared largely static, a frozen mass whose scientific significance lay mainly in its influence on Earth's climate system. Over the past several decades, however, a different picture has emerged. Radar imaging, satellite measurements, and drilling programs have revealed that Antarctica's ice sheet conceals a vast hydrological system composed of lakes, channels, and circulating water moving slowly beneath the ice. Some of these lakes, such as Lake Vostok, are immense bodies of water sealed beneath kilometers of ice and isolated from the surface environment for potentially millions of years. Within these dark environments, microbial life appears capable of surviving through chemosynthetic metabolisms that draw energy from chemical reactions rather than sunlight. These discoveries alter the context in which Antarctica is studied. The continent is not merely a frozen surface environment. Beneath its ice sheet exists a layered system in which ice overlies liquid water, which in turn interacts with bedrock and geothermal heat. This architecture, ice above, ocean below, rock beneath, is strikingly similar to the structure scientists believe exists on several icy moons within the outer solar system. The central thesis of this essay, therefore, follows from that comparison. Antarctica's subglacial lakes represent one of the closest terrestrial analogues to the ocean environments believed to exist on icy moons such as Europa and Enceladus. Studying these Antarctic systems allows scientists to investigate how water, chemistry, geology, and life interact in environments sealed beneath thick layers of ice, conditions that may be common throughout the solar system. In this sense, Antarctica is not only a continent of ice, it is also a natural laboratory for understanding the hidden oceans that may exist far beyond Earth. Understanding Antarctica's subglacial environments changes how several scientific questions are approached, both on Earth and beyond it. The first implication concerns the limits of life. For much of the 20th century, biological productivity on Earth was assumed to depend ultimately on sunlight. Photosynthesis powered the base of most ecosystems, and environments cut off from solar energy were thought to be largely sterile. The discovery of chemosynthetic ecosystems in deep ocean hydrothermal vents challenged that assumption by demonstrating that life can be sustained entirely through chemical energy derived from water-rock interactions. Antarctica's subglacial lakes extend that insight further. These environments are not only dark, but also sealed beneath kilometers of ice and isolated from the atmosphere. Yet microbial communities appear capable of persisting there, metabolizing chemical compounds released from sediments and mineral interactions beneath the ice sheet. If life can survive under these conditions on Earth, then environments previously considered marginal or uninhabitable may in fact support biological activity. A second implication concerns the distribution of habitable environments within the solar system. For decades, the search for extraterrestrial life focused primarily on planets located within the habitable zone, where surface temperatures allow liquid water to exist. However, the discovery of subsurface oceans on icy moons has shifted attention toward environments where water is insulated beneath thick ice layers and maintained in liquid form through internal heating processes. Antarctica's subglacial lakes demonstrate that such environments can host active hydrological systems and potentially viable ecosystems. They therefore provide a terrestrial analog that helps researchers understand how life might operate in the subsurface oceans of distant planetary bodies. A third implication concerns the methods used to explore such environments. Accessing subglacial lakes beneath Antarctica requires drilling through kilometers of ice while preventing contamination of the underlying water systems. These technological and procedural challenges mirror those that future planetary missions will face if they attempt to access subsurface oceans on moons like Europa or Enceladus. By developing techniques for sterile drilling, remote sensing, and microbial detection in Antarctic subglacial environments, scientists are effectively rehearsing the strategies that may eventually be used in extraterrestrial exploration. Did you enjoy this video? Let me know in the comments below. Like and subscribe for more.